quasi-thermal equilibrium state, it can't actually be in that state because there's no incoming radiation to balance the outgoing. So it's not thermally in equilibrium, but it can be in a state close to that called local thermodynamic equilibrium. But in addition to that, and that's a relatively low energy phenomenon, 6,000 Kelvin on the sun, 10,000 Kelvin, 12,000 in an O star, 3,000 Kelvin in an M star, things like this. But now, going to the presence of the magnetic field, something magical happens, and we get this thing that many of us looked at a couple of weeks ago, which is the corona of the sun. So what that is, that's a place where the emission, the emission of radiation from the star is not streaming out from this thin layer, but it's being heated up. And so you have this tenuous hot plasma for reasons which are qualitatively understood, but not really quantitatively understood yet. So I'm not advancing online. No, they're not advancing online, Matthias, not yet. So by way of introduction then, what I'm going to talk about, we're going to get through to the end of this thing by being able to talk about the formation of the photospheric spectrum, but also the coronal spectrum. So we go from very high densities to very low densities. And this is basically the scheme, and we'll go as slow as we like. Please interrupt at any time. I'm here for you guys. This is not for my benefit. This is just for the benefit of people who are interested in, hearing a little bit of physics, interpreting what we do in a place like HAO. Photospheric work, chromospheric work, transition region corona, solar wind. And when we remotely sense these things, what I want by the end of all this is to give you a feeling so you can go out to any kind of meeting in astronomy and say, oh, that looks like the chromosphere. It could be an active galactic nucleus, but it looks like the chromosphere. And there are reasons why that is. And I want to be able to help you understand why those are. And it all comes down to the nuts and bolts. So we're going to talk about, first of all, why use spectroscopy? And we'll have a little bit of fun today. And then we'll get a little bit more serious with the spectroscopy and how it applies to modern solar physics. And then we'll talk about the nuts and bolts of the quantum mechanics of an isolated atom. There's one atom in the universe, and it's not interacting with anything. The interactions are going to be electromagnetic. That's all there is. Once you're done with gravity on the large scales, I'm not going to talk about nuclear forces of any kind, nothing like that. Of course, you can have transitions in nuclear forces, all quantum mechanics with gamma rays and stuff like that, but that's not part of the subject here. We're going to talk about isolated atoms. So it's a bit like chemistry, except because that's about electrons moving around in solutions and what have you, and the interaction of the electron clouds with other things. We're going to talk about that, but embedded in what's called a plasma. And then we'll talk about the thermodynamics of the atomic ions in plasmas, things like reversible versus irreversible processes, local thermodynamic equilibrium, all this kind of stuff, detailed balance. These will become hopefully clear. And then I'll talk a little bit in a very elementary way as a guide to redshift transfer. Now, redshift transfer is a large subject with lots of stuff in it. Very much numerically understood these days, but I'm going to give you a sort of analytic picture of how to understand what happens as the photons are moving around inside a plasma. Okay, and then at the very end we'll talk about atomic spectroscopy. Next slide, please. These are my favorite resources. I will make what of these I can available. I believe the first three, I know the third one is online. There is all PDFs available. So I will make them available in a particular place. The last one, Kurganov, is a way to understand redshift transfer and also neutron transport. Turns out to be the same kind of problem. And that's basically the business of the interaction of electromagnetic radiation with these charges in an atmosphere or a plasma. Okay, and that's going to be analytical because there are certain ways of looking at the way redshift transfer works in transporting energy through a complicated structure. And there are certain ways that I like to think of it in terms of what is called an integral equation rather than a differential equation. The integral equation approach, you can use them both numerically. The integral equation approach is not really used these days. to derive radiative transfer calculations. And what's radiative transfer about? It's about the coupling between two sets of fluids, if you like. One is the plasma, and the other one is the photon pool. You have a pool of photons, and these things are linked together. And radiative transfer is all about how this affects that, and that affects this. So it's Tweedledum and Tweedledee. And the whole basis of radiative transfer is that sun somehow knows how to make its equilibrium between these two things. And it's our job to try and understand how that works. And the emergent radiation then reflects how those things have, those two pools of energy, photons and particles, have ultimately decoupled and produced this spectrum that we see from a long way away. These resources I'll make available. I would say the Cooper first one is a very nice, complete discussion about the embedding of atoms like hydrogen, oxygen, iron 9, you name it. It's all in there in 1966. It is complete up to the point where something called dielectronic recombination became very important to resolve the discrepancy in understanding spectra of the corona. It's not complete when it comes to discussion of how finite densities affect that process. This process we'll get to somewhere in one of these lectures, in one of these talks. Dufton and Kingston is a very nice thing to look at if you're interested in the nuts and bolts of how cross-sections, how atoms interact quantitatively with the photons and with the electrons. So that's a place to start if you're interested in learning, for instance, you know, why is a certain ratio of two emission lines that people study in the ionosphere and the chromosphere, why is it sensitive to temperature? Why is it sensitive to density? And how they vary with charge. One of the really neat things about spectroscopy is, as you remember from the work by people like Balmer way back in the spectra of hydrogen, the early studies of quantum mechanics, before quantum mechanics, they had these patterns, right? And it's the energy minus 1 over n squared, if you remember your quantum mechanics for the hydrogen levels, right? This is very, very regular in frequency. So this is like DNA our DNA was for the 19th century people, you know, the spectroscopy. So they knew for sure that hydrogen was in the atmosphere of the sun, right? But the lines were weak, and they didn't know how much of it there was. That took until 1930 or so for Cecilia Payne-Koposchkin to actually figure out what that meant. So anyway, Dufton and Kingston talk about those regularities, but in much more complicated spectra, when you have multiple electrons. The spectra, we'll see in a minute, are going to be, well, I'm going very slowly at the beginning here, but we're going to see some nice pictures of spectra. And they talk about complicated atoms, but you can still see these regularities. So I can go in the solar spectrum, I can say, here's hydrogen Lyman alpha, helium with 1 electron around it. There's the helium line, that's 304 angstrom. That's exactly 1/4 of the wavelength of Lyman alpha. And the reason for that is because you've got 2 charges in the middle of the helium atom versus 1 in hydrogen. So you've got 4 times the energy. It's the charge squared. So, and then I could go to lithium. I would find another one. That would be 3. So that would be 9 times smaller in wavelength. I go to beryllium and so on, until I go all the way down to the X-rays, and I do calcium 20, and that's down in the X-ray region, but it's still Lyman alpha, okay? It's still the same damn transition. It's an n equals 2 to n equals 1 transition of a charge, and it's going to radiate at enormously long wavelengths if the charge is small. Lyman alpha is the thing that powers half from the mesosphere of the Earth on Earth. A lot of the energy is dumped into the mesosphere by Lyman alpha. And then these other transitions of things like carbon, silicon, and all these other ones with a few electrons removed, those contribute and make the thermosphere. So these things are really the patterns. What I'm trying to get at is the patterns are there. They're easy to understand, and I'll point out some of them. Okay, next slide, please. We're going to go a lot quicker now. So what is plasma spectroscopy? Well, atomic ions are not in a vacuum. There's not just one atom in the universe. That's an idealization we make when we're doing quantum mechanics. Now, if you're far enough away and you put a hydrogen atom in the middle of interstellar space, that's a pretty damn good approximation. So it's not surprising that when you observe through interstellar space and you observe a bright object, you see hydrogen has taken a nick out of that radiation at a particular wavelength. So what is plasma spectroscopy? Here are various plasmas. One is a supernova remnant, one is lightning. The bottom left is the sun. And here we see the peculiarity of the sun is, and it's still a mystery as to why only certain of those loops are full of plasma and why other ones are not. And that still remains to be explained, something I'm interested in personally. But what's going on here is here we're looking at the light in various colors and images from the surface of the sun, which is that mottled appearance, and then the overlying corona of the sun. Okay, so it's departures from what an ordinary atom would do in a vacuum that allow us to tell us what that material is going on in outer space. What's the nature of the plasma? So, in a plasma, okay, if you're familiar with plasmas, if you're not, look at the air around you and breathe it in. And imagine heating that up a lot by some process. First of all, the oxygen and nitrogen atoms will dissociate. And if you keep going and heating it or irradiating it with something like UV, you'll start to knock electrons off those individual atoms, and you'll generate, and that takes a lot of energy, right? That's typically, what, 13 electron volts for hydrogen. What that corresponds to is about 10 to the 5 Kelvin if you were to convert that into a mean temperature of the same. There's a plasma with a mean temperature with the same energy as that, right? So we're talking really hot here. We're at 300 Kelvin. You know, we're talking 2 to 4 orders of magnitude larger than that in order to create a plasma. It does depend on the density, because if the density is very high, if there's a lot of particles there, it's going to take a lot more energy to get rid of most of those electrons off those things. So what do we have? We have in a plasma, you've got a temperature, a density. We know we have some element abundances in the universe. We know we have thermal motions, but we also know that a lot of these plasmas that we can see in space can't possibly be in equilibrium. So there's going to be some motions. And the reason for that is there's an imbalance. The radiation is coming out of these things, but there's nothing coming back to balance that. And what you tend to get then is trigger instabilities like convective instability, which causes the sun's interior to start convecting energy instead of radiating it. Magnetic and electric fields. The electric fields in a plasma are very difficult to sustain on a large scale. You can have microfields. In fact, you expect them. The thermal motions of the electrons in the plasma that whiz around and follow all the atoms everywhere, the ionized particles. Those are all stochastic motions. They're all thermal motions, right? And so you're going to have instantaneous electric fields there. But when I average those out, the electric field goes to roughly 0 in those loops we saw in the sun. The reason for that is simply that if I try to put a voltage across a part of this, like a copper wire, the voltage here is going to be the same as it is there. There's no electric field because it's an almost perfect conductor. And so the nature of a plasma is to cancel out the electric field. So that's the first order thing we don't have to worry about. Magnetic fields, on the other hand, they don't give a damn about the plasma. There's no div B equals a source term. And once you've got a magnetic field, it's very difficult to get rid of it on large scales. So you've got a large scale magnetic field. Okay. This all assumes that we've got a certain particle distribution function. What does that mean? That means, remember your statistical mechanics, and remember that you have a Boltzmann distribution for distribution of occupation numbers of various states involved in a quantum mechanical system. Even classically, when you have a free particles like the electrons here, those will end up with a thermal distribution, providing they collide quick enough compared with computing processes. in something like the interior of the sun, the collision times are ridiculously small. I mean, I don't know what they are, 10 to the minus something, n is 20 or something, I don't know. Even in the corona, the collision time where the densities are really, really low, something like 11 orders of magnitude less than the air we breathe. So it's a very, very good vacuum. There's enough electrons there to conduct the electricity around, and yet even there, the electrons collide with each other once every couple of seconds. So when we observe a large plasma that takes a long time for us to, takes a long time for a disturbance to propagate through. Even if this disturbance along our line of sight is sort of affecting the electrons very quickly, in the timescale of a second, relax to a thermal state. Okay. The ions take a lot longer because they're heavier. They move slower, there are fewer collisions, but they have the similar kind of charge. One electron, one proton. One electron, a nitrogen, fully ionized nitrogen has 7 charges, so it's got a much stronger Coulomb force between them. So the random motions will collide faster. But even so, one has a good chance that the distribution functions are actually close to thermal. That means that if we want to compute the spectrum of something, I can stick in a thermal assumption and see if it works for the electrons. We don't need it for the ions because they're moving much slower anyway for a given amount of energy partition between them. Okay, next click. So what is plasma? There we have a plasma. Now we add to this, the next click. We have an interaction, as I said, between the plasma itself and the atoms embedded in it. So let's imagine having ourselves a little hydrogen atom embedded in this plasma, like a chromosphere, prominence, whatever it is. Okay, now if we want to figure out the interaction of the radiation that's coming from the surface of the sun, that's generated locally by collisions of electrons or protons with hydrogen atoms, etc., then what we're going to have to do is we're going to have to figure out the individual quantum mechanics of, namely the wave function. You have an initial state, you have an operator, and you have a final state. And so when your initial state is, say, the ground state of hydrogen, we put in an operator for the electron collisions, and the final state we get can be, well, could be an electron knocked off. That's called ionization, collisional ionization. It could be, well, we could be knocked up to the n equals 2 level, and so that final state, it would end up with one electron and one hydrogen atom only. We would end up with an electron coming in, losing some energy, the electron having a jump up in the hydrogen atom, and then the electron going off with a lower energy, conserving energy and angular momentum, etc. This is sitting there then in the n equals 2 level. Now that thing has a finite lifetime because suddenly it can drop down to the ground state. How does it do that? By it's got to conserve energy. Where does the energy go? It comes out as a photon. So we have a pool of electrons acting on a pool of hydrogen atoms, and when they all mix up and you heat it up, then what you're going to get is you're going to get more electrons, you're going to ionize hydrogen, but also you're going to get radiation out of this thing, in particular from Lyman alpha, and maybe up to n equals 3, that's called Lyman beta, Lyman gamma, so you're going to get this spectrum built up. What is plasma spectroscopy then? Those are the nuts and bolts of the two sets of things we're talking about. Interaction of the atomic systems with the radiation and with the local plasma, and the plasma itself. So next click. That gives us, you can imagine building a plasma on a computer, putting these things in, and what do you get out? You get photons coming out. And you also get heating, and you also get mass motions, all this stuff. But what we can't measure those. We can't go to the Crab Nebula and measure these things. So we only get the light out of it. So the light is going to tell us the intensity of the radiation. That's the 0th order component. That's just the energy. But we know electromagnetic radiation consists of a vector quantity. It has direction, k, and it has magnetic fields, and it has electric fields in the plane perpendicular to that. So that leads us to polarization, depending on whether these various components, how they're related to one another. And so you end up with something called linear polarization, the blue sky, or you end up with circular polarization, which is called which is depends on the phase between the electric fields in an ensemble of these classical waves coming through. Okay, click, please. So now I finally get to the subject of what we're talking about here. Plasma spectroscopy attempts to do all this in reverse, right? So we have a whole century of research doing these things on the right-hand side, atomic data. So once we've got an atom that's isolated, we can assume, providing the density is not too high, it's still there and fairly isolated, but it's impacted by things like electrons and particles on the left-hand side of the plasma. And while we know mostly that the atomic data can come from measurements in the laboratory, a lot of it comes from computations, really a lot of it. Elementary quantum mechanics. No need for us to worry about that. All I can say is that after a century of research of quantum mechanics, we're in pretty good shape. And typically the numbers quantitatively for these radiative and collisional processes, you know them to about 5 to 10%. Sometimes you know them much worse, sometimes you know them much better. So that's pretty good. The things that we don't know are what the plasma is doing. That's the whole point of this, is we recognize that, we can't go in and wave the thermometer around inside the sun, much though Parker Solar Probe is trying to do that, right? It's 10 solar radii out. The entire corona that's visible during eclipse is within probably 2 solar radii, except for the streamers. So Parker is way the hell above the corona, what I call the corona, white light corona. Joe's smirking here.
But still getting into the subalpinic regions.
It is getting into the subalpinic region, and that's a bit more too complicated for this discussion today. So yeah. Anyway, 20 minutes. Good. So the whole point of this is to go backwards. Now, I think what you can see here, so we, for instance, would like to find out what the plasma density is, what the abundances are. This is the whole point of plasma spectroscopy. So you have an isolated atom with its own spectrum on the right-hand side. You assume that that's still relatively isolated, but it's going to mess with the spectrum somewhat. We'll show some examples in just a moment. And then what we're trying to do is to infer these things on the left-hand side. And in solar physics, one of the most interesting things to do is the B and E fields, because you need both of those to cause heating through in the current paradigm of coronal heating. You need both a magnetic field and a local electric field on small scales. But if you look at this, the modern measurements of SDO, etc., iris, that's all to do with temperature, density, abundances, macroscopic velocity, and geometry. Nothing about particle distributions, nothing about the fields. So you're not learning anything about the causes of why the corona is hot by looking at those things. It's only through modeling that you can actually go further than that, which is beyond what I'm talking about here. The actual plasma spectroscopy only tells you certain things, and if you're not measuring the right things, you're not going to learn about what you're interested in. Next slide, please. So here's an example. Please click again. What is this? Well, here are the 3 lines of hydrogen. This is n equals 3 to n equals 2. That's at 4.5 times 10 to the 14 hertz. Then you've got n equals 4 to n equals 2, 6. And then you've got the H, so you've got H alpha, H beta, and H gamma. Very well known. This is a very high pressure plasma. It's got a temperature of about 10 to the 4 Kelvin, and it's got 10 to the 23 particles per meter, about 10 to the 17 particles per cubic centimeter. That's about 8 to 9 orders of magnitude larger than, say, in the corona. It's about the same as right underneath the photosphere, really, really thick, dense plasma. And what you can see there is that only 3 of those lines are visible, but you know there's lots more. You've got n equals 5, 6, 7, 8. They've all gone. And what's pointed out here by Fujimoto, who has a nice book on this subject, is that the lines kind of, if you extrapolate and join up the H alpha, H beta, H gamma, and then you go, there's a slight hint of H delta there, right? But then you've got this continuum. That's exactly the effect of the dense plasma on the hydrogen spectrum. It smears out the hell out of the spectrum because the lifetimes of the levels in the upper levels of these radiating atoms are affected by a huge number of collisions with the local particles in the plasma. The plasma has caused that spectra to get rid of all the other high-end lines, and it's the effect of the plasma. So what you can do is you can put a probe in, and that's what they did in this experiment, measured the temperature, they measured the density, and then you can go back and calculate with your hydrogen, all your cross sections and everything like that, what you expect to see. And this is what you'd expect to see, amazingly enough. Next slide. So now we go and we look at the same thing, but we look at something on the sun. And we look a little bit above the limb. And this is from Skylab, one of my favorite things. It's Skylab flew and dumped into the ocean before most of you were born. So, you know, but I remember it very well. And what we're seeing here is n equals 16 through about 30 Boulder lines. So the effect of this plasma is to make the lines hardly broaden at all. But the point where they merge into a continuum, if you've got a spectroscope with enough resolution, tells you about what the density is. Because that point is the place where the collisions between all the higher levels in the atom merge together. They don't affect the lower levels. Why is that? The lower levels in hydrogen are about 1 Bohr radius, right, in size. If you draw the density distribution of the 2p electron, you know, it's about 1 angstrom. Now, if you go with quantum number, that goes with quantum number to some power, like 2. So the n equals 3 level is going to have something like, you know, 4 times the energy, 3 divided by 9 divided by 4, whatever that number is. And as you go higher and higher, the atoms get bigger and bigger and bigger. And by the time you get out there, there's almost no energy holding the particle in. It's almost in a free state, the electron. And what's going on is that as you go to higher and higher quantum numbers, the collisions, if an electron is coming past in the plasma, it can knock these off. It can affect these lines drastically and affect the lifetime. And that's why the spectrum becomes from sharp lines in the low end numbers into a continuum. And we haven't even got to the series limit yet. There's an infinity sign there. That is the official wavelength at which you can ionize hydrogen, right? From the n equals 2 level. But you can see it's already been ionized because of the effect of the plasma. The stuff at longer wavelengths, that the photons don't have enough energy to ionize it. But what this is telling us is that the density is sufficiently low that you see all these sharp lines, but eventually the atoms get big enough that the electrons in the plasma knock them off and they generate this this continuum. And so it's this difference here, n equals 30 to n equals infinity. So you have the principal quantum numbers go from, you know, 30 to 40 to 100 to whatever it is. Those above 30 are not really bound states anymore. They're part of the pool of electrons that are floating around. So what you've done is the plasma has lowered the ionization potential of hydrogen. That's really interesting, and it shows up in the spectrum. So you can tell immediately what the density is from this. Then you can look at these actual line shapes if you have a good enough thing, and you can work out that as the lines get gradually broader because of the impact of the electrons. Why is that? It's because when you have an energy level with a certain lifetime, we know that delta E, delta T is h bar, okay? Basic uncertainty principle, quantum mechanics, okay? So that if we have a delta T of a certain number, like that's the lifetime of that level against some process, then we have the product of delta T times delta E is the constant. So now, if I ask myself, if I have an estimate of the uncertainty in what the energy of that level is, it's h bar over delta T. Now, if I make delta T very small by colliding with electrons, then that lifetime gets smaller. So in effect, the upper level has a very much larger uncertainty because we reduce the lifetime of the level by collisions with the electrons in the plasma. And that's a signature of a plasma spectroscopy. So this is how this, so there's two signatures. One is this blending of these lines here, and the other one is the actual profiles of these kind of lines here. Next slide, please. So here's an example of what I find quite interesting. So I think most of us are aware of this, but there's two people I'd like to introduce you to. One is Josef Fraunhofer, and the other one is Mary Shelley. Now, these are not known to be related in any way, but they are related in a curious way. So, next slide. So here is, I hope some of you recognize this. One of my favorite comedians on the bottom left is Marty Feldman. Just the nicest guy and very strange. But here, what we have here is a convergence of Fraunhofer and, click again, please. Fraunhofer and Mary Shelley, because what we've got here, we've got the creature being energized by some lightning. There's a kite in the sky and there's lightning coming down. So in that lightning bolt that's there, it's going to emit some photons. All right? I mean, you can see it. The photons are there. Okay, click, please. And now if you were to observe those photons with one of Fraunhofer's instruments, then what you might be able to do is find out what the essence of life is. Okay, that's the joke here. I mean, it's so what you're doing, we're using these spectra to diagnose whatever it is that Gene Wilder did to energize this thing and figure out what caused it to come back to life. That's in principle what we could do. Replace that lightning bolt with your favorite object in the sky, and we're going to do the same thing. Okay, next slide, please. So what is a plasma? Here are some laboratory plasmas. Those are those are lightning strikes within, so discharges within of a large exposure of a toroidal plasma device, irradiating, photons in the blue UV region. Next one. Here's another one, and that funny looking thing on the right that looks like somebody's put a Coke bottle in front of the image or something. That's actually the image. That's not been modified at all. That's the plasma. So what they've done is they've taken two images. One is without the device switched on, and the other one is with the device switched on. And you can see different colors and different brightnesses, but that's the difference between the left and right side is the plasma within that device. Okay, next one. So everyday plasmas. This is a arc. Sorry. Yeah, that's all right. That's an arc thing that you would use, for instance, to etch dense materials. I mean, for welding, that kind of thing. You have plasma TV. You have your little plasma-driven light bulb. Next one. And terrestrial plasmas. That thing there on the right, the little arc thing is the re-entry of some vehicle, I think. If you can click again, it might tell us what that is. No. Okay, and here are the other ones, right? So here, the smooth things, the smooth curved things are, of course, the loops in the plasmas in the corona. And the reason they appear smooth there is because of one characteristic of the plasma and one characteristic of the magnetic field. The magnetic field is particularly simple when you go above the surface of the sun. It has to be because there's not a lot of energy in the corona sufficient to drive electric currents to make the magnetic field anything other than relatively smooth. So it's like looking at a bar magnet, and the iron filings are coming out from the surface of the sun, and they're tracing out the field lines. And the reason they are all lit up like that is because not only is the plasma highly electrically conducting, but it's also highly thermally conducting. It's the same process. In an electron carrying, moving against ions carrying an electric current, constituting electric current, in the same way that moving electron is carrying some of its energy with it. And so that energy is transported because the electrons are so light and impact each other so well. What's happening is, once you heat up part of this magnetic field, within and these are megameters apart, these things, bigger than sort of the size of the Earth, or bigger. And so once you light up part of that with plasma, what happens is the electrons say, hey, I'm really hot over here, you're cold over there, we got to get into some kind of equilibrium state. So what happens is it conducts heat as well as electricity and starts to level out. It won't allow you to build a huge temperature gradient in this thing. And instead, what happens is the electrons get very hot all the way along, they impact the lower atmosphere, and then that heats up and brings more electrons in. You need more energy to sustain that, but initially that is something you can observe happening. So anyway, that generally explains what's going on here. Next one. The scale of these things is ridiculous. 100 kiloparsecs, 300,000 light years is bigger than our galaxy, okay, by a considerable amount. So I think we should probably stop here. These can go on. I mean, this is a very slow introduction to what we'll talk about later in more detail. But what we'll talk about next will be, if you can just go through and I'll tell you so if you can go ahead. So here are some numbers for hydrogen plasma. One of my favorite reviews is by Berginski, a very famous review. Next one, plasma parameters, what constitutes a plasma. Next one, range of characteristics. To the top left, we have very dense, energetic things. Cool things. Bottom right. So you can see various plasmas put in, and this spans 20 orders of magnitude on the y-axis, and then it spans energy of 10 to the 7 on the x-axis. Next one, characteristics of plasmas, keep going, yeah, versus gases. So Y spectroscopy, carry on. This guy said it wasn't useful, and then around the same time, notice that 1835 was after the invention of the spectroscope and analysis by Fraunhofer. He was very Comte was very sure of himself that the only things you could really appreciate in life were the things that you can touch, that you can understand. He was not into remote sensing, but he was proven wrong. He was a brilliant philosopher, but he was called a logical positivist. Next one, Kirchhoff next. That's the beginning of spectroscopy. Next, characteristics of the spectrum, keep going. Yep, and more kinds of plasmas that we're talking about. Eddington, astrophysics, keep going. And here we get to some instruments today. Those are AIA. I don't know what ESP is. Yeah, keep going. Iris. So, these look like fairly random things, but they're not. It's a superposition of fairly regular things, but because they come from different elements, the order is not particularly clear just from looking at those things. Next. Yeah, so what we'll talk about next will be absorption versus emission lines. That's a spectrum of the sun. You might say to me there, oh, magnesium 2 is an emission line. But in fact, only the very, very core is, and it's a strong absorption line at 2800 angstrom that Iris observes. How to get quantitative numbers. This will be the lecture after the one coming up. We want to talk about the formation of these very strong lines in the sun. Fraunhofer observed these strong lines, and then keep going. Some of the systematics. Here is a plot of the energy of a couple of levels in atoms of interest. This happens to be a boron-like ion. And you have a charge on the left-hand side. This is another one, oscillator strengths. And you can see they vary very smoothly with the ion charge. So here's the order I'm talking about. It's really nice. And it's obvious why it must be the case, because you've got in the Hamiltonian of the atoms, you've got Z squared times the charge divided by R for the potential. So there's Z times R, Z times E squared over R, where Z is the charge of the core of the thing. Next, and then we'll learn about processes. reciprocal processes, etc., redshift transfer at the bottom, and that should do it. I think. Yeah. So if anybody would like to comment on the style of this or what would be useful in the future, either tell me now or you can send an email. This, as I said, it's for you guys. It's physics-based, very much so, as opposed to solar physics-based, which I would say, oh, here's a spicule, here's a surge. The sort of botany of solar physics is something that doesn't interest me at all, but you have to deal with it. Any thoughts? Anybody? Online or Joz has left the meeting. That's not true.
You mentioned that there's an assumption that's holds often about things being in equilibrium.
Yeah.
So you can assume, a certain Gaussian fit to that distribution.
Yeah.
So are you going to talk about where that doesn't work? Or is that beyond the scope of this?
No, I can certainly talk. Yes, I'll be happy to. When I talk about the distribution functions of the free particles, for instance, those are frequently assumed to be thermal, right? And the reason is that the relaxation times, the collisions between so it depends on the plasma. If you have a very tenuous plasma like the interstellar medium, there's so few collisions, but also there's very few photons driving it from the stars that are changing very much. So there may be enough time, even when there's only one particle per cc, for it to relax to a Maxwellian distribution, right? If you go to the corona, it's going to take a second or so for the electrons to do it and about a minute for the ions. So if you have any process that can affect the ion distribution function and push it away from an isotropic thermal distribution, like ion cyclotron resonance, then if an instability, that's a reversible process because you're not colliding or you're not increasing the entropy, you're just changing the shape of the distribution function. But those changes in shape tend to relax via instabilities. And so, yeah, it's the evidence for these things in the solar wind in situ is very, very strong, that there are non-isotropic distribution functions of particles. From spectroscopy, I would say that I wouldn't dare go that far myself, even though some people claim to have found non-thermal distribution functions from some of the lower density plasmas in the sun. So it's a question of collision times versus, and one really, really important thing to note is that these collisions I've been talking about, I didn't talk about the incoming energy of the electrons or the charges, but it's well known that the amount of energy exchanged between two particles as they collide from a Coulomb collision or a 1 over r potential goes as 1 over energy squared. So if you have low energy electrons, they collide relax very quickly. The cross section, the probability of interaction drops as 1 over energy squared. So that means that if you happen to generate, say with some lightning, a bunch of fast electrons, let's say 1 keV in a plasma that's at 1 eV, like the chromosphere, then those will take 10 to the 6 times longer. So it's energy dependent. So if you happen to get something in the wings of a distribution function at high energy, those tend to stay there for a while. And it's only the ones in the core of the distribution which relax very quickly.
Okay.
Yeah.
So in the wind, you were talking about solar wind, because there's the core electrons in the straw.
Yeah.
So is that one of the reasons the straw?
Yes, that persists because they don't collide. The probability for electron-electron interaction with a Coulomb potential, which is what we have, we did an electricity here, the magnetic in non-relativistic plasmas is not important, so you just have to worry about the electric field. So that varies as 1 over the energy of the interacting particles squared. And that is a huge assumption that we make in things like the corona. So we have a heating mechanism. We don't know what it is, we don't even, and then people say, well, we observe emission from these atoms, which we assume are under a Maxwellian distribution, but that is very difficult to test. There's other ways to make the same kind of effects as a tail under distribution. For instance, photons. If you have a lot of UV photons around, that's going to generate a lot of high energy electrons, right? I mean, they knock electrons off hydrogen atoms, and you know, of course, the cross section drops. But it's like if you shone a laser at something, you can make a plasma with a laser at a certain energy, and so you know, if that kind of thing is going on in the sun, then you know, you've just got too many. That inverse problem I mentioned about going from the plasma radiation to studying what the plasma is doing and eventually getting to those distribution functions, which is what I had there. That process is notoriously ill-posed. In other words, going from spectra to physics involves a lot of what they call regularization. Because what we're trying to do is we've got a measurement of, say, 5 line profiles, and you're trying to infer the abundance, the temperature, the density, the velocity, and then right down at the bottom of the list is you don't know what the distribution function is, and that could be, instead of just 4 parameters, you've got an infinite number of parameters depending on the shape of the distribution. It's a continuous function. So you have to do something to go from, to do an inverse problem from the spectra to get down into what the plasma and the fields are doing. And so that's called ill-posedness. Anybody still online have any comments would you like to hear more of this kind of discussion, or would you like more technical, less technical? It's up to you. I mean,
I thought it was a great overview for the first day, Phil. It was a nice level.
Okay, thank you. And that's good to know, because Scott's a very bright guy with a PhD, but he's more in engineering than he is in science. So that's very helpful. Any more? All right, so I don't think, did we record this one?
I recorded it, but not at the beginning. Now I have to figure out what to do with that. I've never recorded.
Talk to Carol, maybe, if you
Yeah,
could.
I just want to make sure I don't lose it.
So if you miss these things, you know, you can welcome to come and talk to me if you're interested on your own. I mean, just send me an email or something and we can chat one way or the other. So, you know, I think it's really important that those of us that don't have much hair on our heads, and what is left there is very thin and white mostly, you know, can help out with the young people, because, you know, since I've been working in this area from about 1988, there's been an awful lot of activity in solar physics. But I think only one really major advancement, I think, in solar physics in terms of understanding. And I'll leave you guessing as to what that is. I'll tell you next time if you're interested. Most solar physics is concerned with have to be very careful. I worry that we've got tools and we use them without necessarily asking the right questions. And those of you that are worried about that kind of thing and think you might like to make a real difference in solar physics, I would suggest, if you can, reading some of the new book that I've written, where I lay out pretty clearly, I think, why just doing more and more of the same kind of measurements is spinning our wheels. So it's an opinion, but I think it's one that's worth hearing if you haven't heard it before. But like everything else, you guys have got to make your own minds up and really enjoy the time ahead of you, because we've got fantastic capabilities with DKIST and all these ground-based telescopes, and then all these spacecraft now and what have you. I mean, it's going to be fun. You guys are going to have a great time. I'm going to be off fly fishing in Scotland probably. All right, thanks everybody. If there's no more.
Thanks, Phil.
Thanks, Phil.
See you next week, hopefully. Thanks, Joan, for doing
Yeah,
that. Thank
sure.
you so
Looks like
much
I
for
can
doing
save
that. This is an official HAO sanctioned computer, but I